Great. Good morning, everyone. So my talk towards hyperscale, high-performance computing with RDMA builds upon Roger's talk. Here's our outline. It's pretty simple. So it's going to continue what he started. I'm going to talk about some of the drivers for bringing RDMA into the data center and the hyperscale data center environments. Some of the trends and directions, as in the technologies that are causing this type and similar technologies to this to be used in the data center. Challenges with running it at scale. And then some of the examples here for the things that you, as network operators, should be concerned about and aware of. And I'll also talk about some of the problems and some of the comparisons of the different implementations of RDMA. So a large data center, huge collection of computers. It could be a small regional data center. It could be a hyperscale data center. Think AWS, GCP, or Azure, for example. These types of environments give you very cheap compute. It's very easy to deploy. It's very high performance. And increasingly, we're seeing high performance workloads migrating to these data centers and clouds. In this slide here, what I show is the top 500 supercomputers. If you guys are familiar with it, it's a list that gets published by the University of Tennessee twice a year. And it lists the top 500 supercomputers, and it lists all the characteristics of. What I'm highlighting here is, in the top slide, that half of the interconnect technology in that space, which has traditionally been HPC-based, InfiniBand or InfiniBand derived, is pretty much moving quite a ways towards standard Ethernet. So 50% of that slide is green. 50% of that slide means that's Ethernet fabric, your standard, custom, 802 Ethernet fabric, okay? Now, on those fabrics, you could be running RoCE. In most cases, it is RoCE and not iWARP per se because of scalability. And in general, these are the standard RDMA technology that you can deploy either in the cloud or on your on-prem data center. RDMA does not equal RoCE, and I'll talk about that in a later slide. RoCE is an implementation of RDMA. iWARP is a separate implementation of RDMA. And a lot of the items that you see on the left-hand side of the top pie chart are derivations of RDMA. So hyperscale. It's no secret that this is a space that's growing like crazy. The major cloud providers have incredible size. Quarter over quarter, they're just deploying tons and tons of systems. And how do you build those environments? Well, you have to keep it cheap. You want to use commodity parts. You want to use commodity switches. You want to use simple devices, simple NICs where possible. Not really applicable in the NIC case. You actually require server NICs for a lot of these workloads. But you try to keep all of the components simple, right? Simple and replaceable. In these data centers, we're seeing an increasing growth of new devices coming online. So traditionally, storage has been slow. GPUs weren't really an offload thing until recently. And FPGAs are now becoming much more common in terms of offloading work. Now, in all of those cases, those are accelerators. Accelerators that bring down your compute costs, as in it's more efficient to do your processing. And networking is surprisingly now the slow part. No matter how much bandwidth you throw at the problem, networking is still the slow part. In storage scenarios, we see that with the advent of SSDs and storage class memory, network latency accounts for over 50% of the latency costs for the operations. In the GPU case and FPGA cases, it's the same thing. My compute is now fully offloaded. It's incredibly fast, and moving data around to the accelerators is what's causing most of my latency. So here's an example putting it in numbers. We see on the left-hand side your standard hard disk, the spinning disk of Rust. That's quite slow in the tens of milliseconds access times. And over time, we've moved to what you see here, NVMe devices over storage class memory, in which case the operations to the disk are extremely fast. it's a 2 microsecond access time, and everything else is really software or communication overhead. If we take the case of accessing that device over the fabric in NVMe over fabrics, which is essentially RDMA directly to SCM, we see that there's a small delta increase in the access time because you're accessing over to the fabric. But it's nowhere near what it was before in terms of millisecond times. So in both of these cases, we're talking sub 10 microseconds or similar access times. A standard application running over kernel-mediated or host-mediated I/O is simply not going to be able to achieve those latency numbers, which means that if you have those accelerators on those devices, you can't actually make use of them unless you have a pipe, a facility, or a tool, as in RDMA or similar direct access technologies, to actually access those devices. Here's an example from your typical HPC scenario. So on the left-hand side, you have your typical MPI job. Job starts, distributes a bunch of work to all the worker nodes, which means a bunch of copies are going all over your fabric. All those worker nodes are processing at the same time, right? And once they complete a job, as in job completion time, that's when the job is done. Any stragglers, slow processes, latencies, drops, congestions, delays, is going to delay your job completion time. From a single processor point of view, right, and application point of view, what you see is if there's a drop or if there's congestion, you have a stall in the pipeline. Yes, my processor can go off and do something else. That's what the scheduler takes care of. The problem is in HPC type workloads, you typically don't run dense multi-tenancy. You typically have a virtual machine that takes the entire physical machine, or you have a physical machine dedicated to just the HPC job. So any delays there, which way they are going to impact the application performance. If you take the example of that single processor and you scale it up to multiple processors, then that just reemphasizes the point that it's really the tail completion time that determines the job completion time and the actual cost. So one has to say, why is that important? To put it into numbers, a lot of these HPC applications, think of fluid dynamics, for example, you're being charged not on a per core basis, but on a per time basis for your usage of the application. In some cases, it can be in the hundreds of thousands of dollars. So it's of the utmost interest that your job completion time be as absolutely small as possible. Microseconds absolutely matter in these types of workloads. Here's an example from storage. Very similar. I'm doing a bunch of transfers. One of the transfers stalls, there's drops, there's congestion, there's a delay in the network, and you can't get the data out to meet the SLAs. So this is a problem. It's simply another spin on the same thing I described earlier for HPC, but in the storage context. So I've described some of the trends, some of the technologies, and some of the issues that are forcing a need to have extremely low and consistent latency in the data center. So how can we achieve that? RDMA is one example. RDMA simply means remote direct memory access. It means I have two endpoints where my layer 4 and layer 3 are fully offloaded onto the NIC. The application is simply managing a set of queues and submitting work requests to execute those transfers. And everything else is taken care of under the covers by the physical NIC. The data from the application is placed directly into the application, meaning that the application will register the exact memory where he wants to write from or read to. There are no intermediate data copies, there's no middleman, there's no host-mediated I/O. And I'll discuss that in more detail in later slides. Now, in the top part of this diagram, this is your standard sockets communication. The key things to keep in mind here is standard socket communication from user space requires a context switch into the kernel and an associated data copy and protocol processing. Those are the three exact things that RDMA eliminates. There's no longer any need to break into the kernel because user space is managing the hardware resources, the queue pairs, and submitting the work requests and completions directly. There's no need to do protocol processing because it's been fully offloaded onto the NIC, as in the NIC should take care of any retransmits or any transport level reliable connectivity operations. And there's no buffer copies because you're not going into the kernel, you're not taking the context switch, and the adapter's taking care of everything for you. So to put it into more context, here's an example. Given two applications with the same fabric, same device, same adapter, obviously fine-tuned to be co-located on the same switch, you should see in a well-tuned environment about 30 microseconds for TCP access time for transfers, right? So that would be 30 microseconds round trip time, okay? If you're doing it through RDMA from application, accessing the resources directly, you are down to 1 microsecond. And in many cases, depending on vendor-specific extensions to your RDMA operations, you can be even below 1 microsecond. Of course, as you scale, the number of switch hops that you have and the bandwidth delay product or distance that you're trying to talk to is really going to determine what your lower bounds are. So ultimately, you're always going to be bound by physics. So I mentioned earlier that RoCE is not RDMA. RoCE is simply an implementation of RDMA. And this is a variation of the slide provided in the previous talk. And what we see here is that the InfiniBand, which has been the traditional HPC mechanism, is really where most of this technology came from. And that in turn evolved from other technologies before that. Now, in the InfiniBand case, there's a layer 2 that is credit-based. So what you would consider a layer 4, as in the InfiniBand transport layer, has the liberty of being quite simple and inefficient because of that simplicity. Because it can rely on a layer 2 that guarantees that there's no loss on the fabric. As that technology moves over on top of Ethernet, we see here in RoCE v1, which was the first implementation of, it simply replaced layer 2 with Ethernet and kept layer 3 as is. Interestingly, layer 3 for InfiniBand has the same exact frame or header format as IPv6, with really the only difference is that the next header values conflict with the IATF or INA defined values. In RoCE v2, then the IP fabric became more standard, meaning I didn't need any special sauce. I have full IP interoperability, and UDP simply gets used as a tunnel. So even though UDP is traditionally layer 4, that's unreliable, in this case it's really just acting as a tunnel, which is not a novel concept. This has been used before. It's the basic concept behind VXLAN, right? Where you have basically multi-level nested virtualization, network virtualization, and your actual transport level operations for reliable connectivity are contained in your inner frame, not your outer frame. Here, it does exactly the same. It simply uses UDP as a tunnel with a well-known destination port, and the actual transport that's taking care of your reliable connectivity is really sitting up right above that in the InfiniBand transport. So that's one implementation of RDMA. Another implementation of RDMA is iWARP. Surprisingly, iWARP does not mean internet-wide RDMA protocol. It's a fallacy. I know the folks who came up with this stuff, and they say that that is absolutely not true. iWARP simply is RDMA operations running over TCP IP. And in this case, you have your standard tried and true TCP IP congestion control algorithms, of course, implemented in vendor-specific ways. It has selective acknowledgement, it has fast retransmits, and it has some benefits that RoCE doesn't have. Both technologies and implementations have their pros and cons. As network operators, you need to be aware of what these are. I encourage you to look at some of the slides in the backup section that have has a lot of references as to the quirks and differences between them. Now, one thing to keep in mind, I mentioned earlier that the InfiniBand layer is lossless. When we bring RoCE or the InfiniBand transport on top of Ethernet, we also have to maintain that losslessness. And that's achieved through data center bridging, specifically priority flow control, enhanced transmission selection, and explicit congestion notification. And I'll talk about all of those in more detail. Now, other things you'll want to be aware of between these two technologies. There's a lot of philosophical debate as to which one is better than the other. Honestly, they both have their pros, they both have their cons. To give you an example, in many cases it's stated that RoCE is simpler than iWARP. It depends on which point of view you're looking at it. Because from a ASIC implementation point of view, RoCE is going to be simpler. It's a very simple transport. There's not a lot of stuff to code in silicon for that. However, it's because really the onus of making that stuff work, having full end-to-end reliability now falls on the operator, not the implementer, which means it would be folks like you guys that become impacted when this type of technology gets deployed, because it requires a lot more hand-holding, a lot more tender loving care in configuring PFC in a perfect way, in configuring ECN in the perfect way. In the case of iWARP, it doesn't actually require any of those technologies. ETS, for example, enhanced transmission selection, which is bandwidth reservation, is equally applicable to both of them. It isn't really a requirement for iWARP. However, it is absolutely a requirement for RoCE. So here's a basic RoCE network to give you an example. So if you have, if you have a flow and you detect congestion on the fabric, in standard ECN parlance, it's going to do forward congestion notification on frames that are transmitting or transitioning any middle boxes. That's going to reach a destination. The destination is then going to detect that congestion was seen somewhere along that path, and it's going to, in the TCP/IP sense, piggyback a message back as part of the ACK to indicate to the source that it needs to throttle or source quench. In the RDMA case, it doesn't actually trigger back a ACK-based piggyback. It simply generates what's called a congestion notification packet that will essentially source quench the specific sending queue pair on the source. And it attempts to throttle and slow down the traffic so as to not exacerbate the congestion that was detected in the first place. Now, ECN is great because it can help you throttle before you get to the worst case, which is stalls. Stalls introduced by PFC. PFC is the worst case scenario, meaning, okay, now I actually have to pause. And what becomes even worse in the PFC case is when you trigger head-of-line blocking, meaning that if you have a middle box, so think of the TOR right before your physical machine. If that egress port to the host becomes congested, and that congestion doesn't clear, and ingress traffic continues coming in, it's going to cause pauses on the ingress port of that switch. And if the same thing repeats, it's going to repeat the same thing to the next hop, and the next hop, and the next hop. You could potentially end up with fabric lockup and victim flows, meaning that flows that which is transitioning any of those middle boxes on those ingress queues or ports for those switches that have nothing to do with the destination they're actually trying to reach will essentially become blocked. And ETS, I'll describe this a bit later, but ETS becomes important in a hyperconverged fabric if you're running RDMA traffic with something else. Think tenant traffic or cluster traffic or anything else that's not RDMA. You essentially need to carve out the bandwidth, as in reserve the minimum bandwidth per traffic class. So congestion control and RoCE. This is important because this is the part where you guys can become affected by having to augment with layer 2 mechanisms. In congestion control and RoCE, it's simplistic. Let's take a very exaggerated case. In RDMA, I can transfer up to 2 gigabytes minus 1 byte in a single transfer. That means my application can say, hey, send this as in a single operation. And he can literally transfer 2 gigabytes minus 1 byte of data, just stream it to the other destination. The way it does that is it doesn't actually do very elaborate sampling for end-to-end to determine if he's going to overload the fabric or not. It doesn't. It just starts to send a lot of traffic at once, and it expects layer 2 to be able to manage that. If there is congestion, or there are drops, or there's a head-of-line blocking case, or any of the examples that I gave previously, it will essentially go back and retransmit from the starting point, of which case the optimization was made to actually do a version of checkpointing in between those 2 gigabytes, which says, hey, maybe for every 256K or or 16 megabytes or whatever size it was. Let me just retransmit from that point. So now it becomes the onus on the operator to configure those NICs in a specific way to determine what checkpoint he wants to determine what the retransmission amount is. That's a bit complex. This is an area that requires a bit more innovation. It's definitely one of the blockers for scalability. It requires significant complexity on fabric configuration to make sure that you have a lossless fabric and that this doesn't happen. Now, there's also the concept of live lock. If you take this example of a partitioned window where you can have loss and it transfers everything from that window back, you can imagine the case where if you had a very high loss network or a network where your losses have a high probability of occurring within the window, you're essentially having live lock, which means you're putting a lot of fabric on the network, you have one loss, and now you're putting everything back. So you've both consumed the bandwidth, blocked something else, and you didn't make forward progress. Live lock by definition. Explicit congestion notification. So this is the key part of making RoCE scale well. It means that you have to take all of the queues on your middle boxes and you have to program the thresholds correctly. It says that you need to account for your worst case scenario RTT, bandwidth delay product, establish a trigger that would allow for detecting when there's congestion up to that point such that you have time to send the message back to the source so it can quench in time, and ideally set at a point that it doesn't do spurious triggering of PFC, which has some of the downsides that I described earlier. In priority-based flow control, so this is the one that we must be careful with. So priority-based flow control is simple. You have global pause. It simply says, now do it on a per traffic class basis, where traffic classes are defined as the 3 bits in the class of service field inside of 802.1p. That's in a subset of 802.1q. Now, you may run into challenges in configuring PFC, and you may run into vendor dependencies. All of the vendors for switches for configuring PFCs have their own unique ways of partitioning the buffers and setting what the thresholds are. And in some cases, you may not have the ability to set the thresholds to your desired configuration. It may just have a general setting for you. Furthermore, a lot of the switches that support PFC may only support PFC for a subset of the traffic classes. It won't support them for all 8. There aren't cases where you actually need all 8 unless you have an extremely complex fabric. In most cases, you need about 2. You would need one for high priority RDMA and low priority RDMA. But if you needed to use more, or you had a very dense mesh fabric where you needed more granularity, you have to be careful with which switches you buy and which capabilities they have. Enhanced transmission selection, this is the part that comes in that gives you the bandwidth reservation. In the most simplest form, you can think of it as if I have an unorchestrated layer 2 implementation, I could essentially have my RDMA traffic overrun my TCP/IP traffic, or vice versa, right? It's common to have TCP/IP, or more properly, unbound UDP preempt RDMA traffic. It's not uncommon. You can easily make this happen. It's as simple as putting DPDK in a VM and just blasting as much DPDK traffic through UDP as you can, and you'll see how it starts to affect everything on the fabric. So enhanced transmission selection essentially gives you 8 lanes, right? It builds on the same traffic classes that I described earlier, and it gives you a minimum bandwidth reservation. And the way it works is simple. Assume that I have a 10 gig pipe. I partition it 50-50. I say 50% reservation for RDMA on traffic class 3, 50% reservation for everything else. In the absence of any 10-inch traffic, RDMA on traffic class 3 could consume its 5 gigs and scale all the way up to 10 gigs. But as soon as the other traffic class starts talking, then it becomes throttled down to a minimum guarantee of the 5 gigs that were initially established. You can partition this up to 8 ways. It can get pretty complex when you start partitioning it. In short, there are challenges with deploying technologies like RDMA. I'd argue that some of those challenges aren't actually RDMA specific in the context of this audience. You can consider any case where you have an overly greedy transport that is not doing end-to-end sampling, that is not being a good citizen on the fabric, that is simply just ramping up his egress traffic to the point that it's disturbing others. There are ways to try to mitigate that. RDMA is by no means the only example. I can give you three. There's AFXDP, which is a mechanism for providing user space near-native hardware access for I/O, meaning that you can bring along any application and it'll just start spewing its own transport. There's DPDK. There's Linux. You can pretty much code up the Linux kernel to do whatever you want. And in general, there are known examples at scale. For example, there's quick internet connections. That's widely deployed. If you think about your typical Chrome browser, it's running quick under the covers, which means it's a user space transport, meaning it's not going over kernel-mediated I/O. It doesn't take too much to have a port of that off of Chromium. That technology for quick is what's used to power a lot of the Google first-party properties, so think YouTube and Gmail. In those technologies, and all of the examples I've just given, these are the non-RDMA cases where you have user space coming in, bringing their own transport, putting traffic on the fabric, and potentially causing disruption and noise. As network operators, you have a set of tools at hand to try to mitigate this. We have potential tools in layer 2 trying to use PFC and ECN, and you have traffic shaping. You can do traffic shaping or egress limits in QoS. These are a lot of interesting areas that could be used to try to bring more order to this new world where transports require extremely low latency, new devices coming on board require extremely low latency, and you need consistency at scale. And lastly, here we are. So I've talked about RDMA, some of the new technologies coming on board in terms of storage, CPUs, FPGAs requiring the need for extremely low latency and consistency. I've talked about the high-level operation of RDMA, how it works and how it contrasts between RoCE and iWARP. And I've talked about some of the challenges for configuring and operating RDMA. This is an area of a lot of research and investigation. This is an area where you just go survey the papers, and there are tons and tons of papers on transport innovations in this space. A lot more work is needed here. I have high hopes for delay-based congestion control protocols. But those types of congestion control protocols should, in theory, minimize the need for having to use fabric-based feedback mechanisms like ECN or PFC. There are many examples of such. Timely is one of the examples. I encourage you to read one of the Timely papers. It's in the reference section for this document. And with that, this is the end of my talk, and I'll take any questions.
Hi, Rob Seastrom, stepping back from the mic and not making it explode this time, asking a question on my own behalf. One of your first slides had a quote from Mr. Huang, CEO of NVIDIA, that said that in the future, all data centers are going to be built like supercomputers today. And I may not have been paying close enough attention, but I don't think that you touched on the subject of crypto here. And as we know from the Snowden disclosures and Muscular in particular, if you think that the network links between your individual elements are secure, you're probably wrong. So I was wondering if this is in the roadmap, if this is something that's going to get hastily bolted on after the fact to make everybody sad, or something that nobody has given any thought to.
Absolutely critically important area. Extremely important. Not covered in my talk, simply because this is more about latency and performance, excluding security.
Yes, but if you add crypto in the middle, it hits your latency and performance, so it's something.
Yeah, agree. I was going to cover that part. In the RDMA case, based on the current protocols, think of RoCE and iWARP, it's a bit difficult to bolt on security at the moment. That's one of the reasons why you don't see it widely deployed to tenant endpoints, right? So for example, in Windows Server specifically, we support RDMA to guests on-prem, however, not in Azure proper, at least not yet. The reasons for that are really because it comes down to security. You want to secure and encrypt that traffic. What is happening in this space in terms of security expands beyond RDMA. If you look at QUIC as a protocol, it's encrypted by nature. If there's no encryption, it's simply not going to work. You have to fall back to TCP/IP. In the case of RDMA, really the innovation on encryption is coming into inline encryption processing. So one of the
on the network cards themselves.
On the network card or through middle box proxy. So you can think of cases where, and this is no secret, the cloud providers are all looking at this. How do they add specialized silicon to do inline processing at minimal cost, fully in hardware, for any transfers that are occurring between any two systems? Now, the challenges in that are that there may be cases in RDMA where more innovation is required. For your standard TCP/IP, UDP transfer cases, regardless of what the application is, it's fairly simple. But in the RDMA cases, there are some challenges that still need to be figured out.
I'm heartened to hear it's on the roadmap. Thank you.
Hi, my name is Anand from Dell. I have just want to pick your brain. So between RoCE v2 over iWARP, which one do you think will gain more traction going forward?
So that gets into the philosophical war that I mentioned earlier. I can give you the company answer, which is we don't have a preference over either one. The personal answer is it really depends on the scale. It really depends on what you're doing. To give you an example, it also depends on the workload, of course. If you're doing small scale, let's say you're doing small regional data center, something small. In most cases, iWARP will suffice. Why? It's simply simpler. I don't have to have a specialized layer 2 or specially configured layer 2 for it to work. You would only decorate or enhance L2 if you want to make it better, if you want to have better SLAs, if you want better storage over iWARP, as in 50% of my bandwidth is storage, 50% of my bandwidth is other, simple examples, and I want that strict line to be consistent. Those are the cases that you would add DCB PFC. RoCE, however, for the most basic operation, even a 3-node cluster running on the same common switch, would require very delicate configuration of all of those values. ECN comes into the picture when you're doing multi-hop and routing, of course, but you would still have to require PFC. So from that point of view, I think it really depends on the scenario. If you're going maximum scale, if you're going like, a couple of dozen rows, hundreds of servers, you most likely have a network operator who's expected to be specialized and knowledgeable in this space and can configure PFC and ECN accordingly, and in that case, it would work. Again, depends on the scenario. Thank you.